Hello, hello, hello. I think I'm in the loudest room I've ever been in. This, of course, is Mr. Folly, which fits well when we start talking about entropy and sign change. Entropy is what Michael's been waiting to talk about, and we've all been waiting to hear about all year long. Entropy is abbreviated S. Entropy is the energy loss to disorder in a system. So no one ever uses that. It's chaos. It's messiness. Whoops. It's confusion. It's any way it becomes an increased complexity. Okay? So chaos, believe it or not, always increases. Okay. So 90% of the questions, the way you answered is more gases increase chaos, thus increase entropy. And that's the answer to what has more entropy. Okay? So, sorry, I laid on my cough button. This is a solid. Oh, I said it's a solid. Has the least entropy, then a liquid, then a gas. Now, no kidding here, right? Solid has the least chaos. A liquid is medium in messiness, and a gas has the greatest complexity and mixability. Okay, so notice a solid is 1, liquid is 1.3, and a gas is hundreds of times more. Okay, now aqueous is a big pain in the behind. Aqueous is where it's dissolved. Okay, so if I'm looking at this, this looks neat and ordered, right? It is a solid. But this also has a bunch of water that's a little scrambled around. Okay, so aqueous is usually more disordered. So this is a solid. This has low S. Okay, I'm going to put delta S because you usually see delta S, but in most cases, but I'm going to leave this as S. Low entropy. The liquid has medium entropy. Now, when I put it together, do you see how this is kind of neat and organized, right? So if I told you that when you combine the low solid and medium solid, do you see how maybe it could be a little closer to one way or the other? But what you need to know is expectation. Aqueous, usually more disorder. Chemistry is not chemistry unless it has an exception, and it will tell you pretty clearly it's not. Most dissolving is more disordered, but maybe you could see how water might be more organized and have slightly bigger delta S. So what is entropy again? Chaos and messiness. Low chaos and messiness, higher chaos and messiness. Delta S goes up. I put highest because I'm talking about S. More particles means more entropy. What's a bigger mess? What's more chaos? 10, well, let's do simple. What's messier and has a bigger mess in the house? 2 dogs or 15 dogs? 15 dogs is more chaos. More dispersed means more entropy. What's more chaos? What's more craziness? If I have 2 dogs in the bathroom, I'm assuming that's the smallest room in your house, or, well, let's go 15 dogs. 15 dogs in the bathroom or 15 dogs in a field. If you want to recollect all the dogs and organize them in a field, it's way harder, okay? Volume of gases increasing equals more shuffleability. So notice, not the amount, volume. Okay, mole's a little different, but that's it. More shuffleability and thus more chaos and more entropy. Of gases, right? This is gases only because that's the only time. So again, that's pretty much what I showed you. That's more dispersed. Do you see how more dispersed means you basically have a bigger volume? Those are same. Increasing temperature increases entropy. So what makes a bigger mess? 15 dogs in a bathroom or 15 crazy rabid dogs? I almost misspelled rabid. Rabid dogs. 15 rabid would have more because they have more energy. They're going, they're all over each other until they're dead, in which case they would have less entropy. So dead things have low entropy. Aww. All right, 9.3, Gibbs free energy and spontaneity. Thermodynamic favorability. Gibbs free energy, that's delta G. Gibbs free energy is delta G. The degree sign means it's in the standard state, which is 1 atmosphere, 298 K, and molarity is 1. This barely matters. We might be able to get through the whole year without that ever coming up. Okay? All right. Spontaneous, which means that it's thermodynamically favors, which means the reaction will happen. It will happen. It's going to happen. You cannot stop it. Okay? This happens when delta G is negative. It will happen. If delta G is negative, it will happen. Doesn't mean it'll happen quickly, but it will happen. It may have to overcome EA, activation energy. Activation energy is called our kinetic control. So it may not start. This does not mean it is at equilibrium. If a reaction is known to occur, thermodynamically favorable, and doesn't occur at a measurable rate, it is due to a high EA. This, every bit of this is 9.4. That's it. That's all 9.4 is. Delta G is negative for spontaneous reactions. Now, means if it's something spontaneous, that means it will happen. So I could say that clearly, Molly is the most spontaneous person in the room. Why? Because Molly throws things every time I turn my back to the board. Molly yells out, "No way, you got to be kidding me." Okay, well, maybe Molly doesn't do that, but that's what spontaneity means. It means it's going to happen. If I turn my back, will Molly throw something in this fictional scenario? Yes, she will. If I don't, she won't. Okay, does that make sense? Now, then we have the calm person who never does anything and never, ever talks or questions anything in class. Let's call that person Michael. Now, Michael, just because something's non-spontaneous doesn't mean it can't happen. You could give Michael $1,000 to do something crazy, and he'd do it. Or you could give Michael, I don't know what else would inspire Michael. No, I should know what else inspires Michael, but whatever inspires Michael, he would do it. But it takes energy to do that. If delta G is positive, the reverse reaction will occur. Bold above is the annoying consideration. So remember this. This means unless EA reverse is high. Okay? So this is the worst thing on earth. So a lot of times, probably the easiest one for spontaneity is I have a boulder on a hill. Will this boulder spontaneously roll down the hill? Yes. And I have a little wedge in there. This is my activation energy. If I pull out the wedge, it will roll down the hill. Now, will the boulder spontaneously roll up the hill? Rolling up the hill, delta G is positive. That means not only will it not happen, the reverse reaction is going to happen. Does that make sense? So it's not just that it's not going to happen. That means it's the opposite's going to happen. Okay? If delta G is at 0, the reaction is at equilibrium. Okay? Now I want to add something in a angry color so you remember it. So includes phase changes. Anytime you are in a phase change, delta G is 0. Okay? That means the phase change has to happen at the boiling point or melting point. Your phase change is going to have a delta G of 0. It is extremely forgettable. People miss points on that. It makes me sad all the time. I will trick you on it just like what changes K? Temperature. Okay? The equations that we use for delta G are very common. Delta G is products minus reactants. So you can see that both delta H, enthalpy and heat, and delta S, chaos, impact delta G. And a lot of times we just care if it's going to be negative or positive. Okay? The equation, delta G equals delta H minus T delta S, is most often used to indicate if something is spontaneous or not. Algebraically, we can tell that delta H would contribute to thermofavorability. So if I have delta G equals delta H minus T delta S, T has to be in Kelvin, so it's going to be a positive number. So if my dream is to make this negative, what would I have delta H be? Well, delta H would be negative. That would be most likely to make that negative. Minus what? Now, if it's minus a negative makes a plus a positive. Oh no, that's not it at all. Nope. So if I want it to be spontaneous, it's going to be minus a positive. Okay? So algebraically, we can tell that delta S would contribute to thermodynamic favorability. You can just say algebraically, or you can do the math. This is one where I do the math all the time. Okay. So right here, if we have delta H, most often you see this with a negative sign. This would be a positive sign, negative sign, positive sign, negative sign, positive sign. Oh, negative sign is still there. Okay. So if delta H is negative and delta S is positive, it's favored at all T. That means it's always negative delta G. So this is, I don't like no T, never. You can never make it happen. This will never be spontaneous. Oh, how sad. High temperature. This means delta G is negative, which means it's spontaneous, only at high temperatures. So think of something like melting ice. Melting ice is only spontaneous at higher temperatures. So this means delta G is negative, which is spontaneous, only at low temperatures. So the easiest one to think about for this is freezing water. Okay. This analysis can help us predict thermodynamic favorability, spontaneity, by stating endo, exo, and predicting delta S based on states. And it is important to note that delta S is often close to zero and doesn't matter. Okay. All right. So when we're doing predicting whether it's going to be spontaneous or not, okay, you count the number of gases using coefficients. All right. So in this case, the delta H of elements, their standard state is zero. I think we did this before, right? So when we calculate delta H, these are the things that you need to remember. All right. Delta G of elements, their standard state is zero. Delta S is never zero. It's only zero for a perfect crystal at absolute zero, which is 0 Kelvin. S is not zero ever, 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 ever. Okay. Example. The decomposition of hydrogen peroxide, H2O2, occurs slowly at room temperature according to the following temperature. Now it says it occurs slowly. That means delta G is negative. Okay? Why? It occurs. Okay? Now, that's the best way to do it, right? Solutions. Oh my goodness. Here we go again. You guys always get mad at me. This keeps coming back and keeps coming back and keeps coming back, and you keep saying we never do it. We're talking about particles breaking. Intermolecular particles between solvent particles are overcome. Okay? So when you are breaking solvent to solvent, that's a positive delta H. Okay? If you are separating solvent, that is a positive delta S. Intermolecular force between solute particles, I'm breaking bonds. I'm spreading out. Okay? Intermolecular force between solvent and solute particles form. I'm forming bonds. I'm getting closer together. So do you see how those things it depends on the magnitude of each one to tell whether it's going to be spontaneous or not. So not everything dissolves, right? So if I have particles that are bonded together and the solute particles are wicked strong, I'm wicked strong. This could be so large that it will mess up everything. All right. Which solution would have greater entropy with all other factors remaining equal? Justify your answer. All right. Greater entropy. So most chaos. All right. So I have CaOH taken twice, BeOH taken twice. Saturated solution. Okay, so I notice this K right here and this K right here. So this one has more dissolved. So aqueous has a greater S than solid. So delta S is larger for more soluble salt. Okay, Remember, we're supposed to assume that it is increased unless it gives you strong evidence it's not. So remember, a big K means lots of products. Smaller K means less products. Delta S favors, delta S increases, right? Delta S increases. So it's thermodynamically favorable. Okay. All righty. I think, nope, we got a little bit more. Ooh. Oops, this last part. Hess's law and entropy include coefficients. So all we're going to do here is a little bit of math. Okay. So the equation is Hess's law. Reaction equals products minus reactants. Reaction equals products minus reactants. Reaction equals products minus reactants. Sigma means summation of, include your coefficients. Here's a table of annoying, okay? And we're going to look at these and do a couple, okay? Find delta S for this reaction. Delta S is products minus reactants, okay? So my reaction is going to be zinc nitrate aqueous. I'm going to put my little coders down here, so it's GHS. GHS. Okay, so zinc nitrate aqueous was 181. NaOH aqueous is 11.9. Notice how these cannot be negative. Zinc hydroxide is 81.2 because you can't have a negative for delta. You can't have a negative for S formation. It's rare, I guess I shouldn't say can't. NaNO3, NaNO3 is 207. So what we're going to do is do products minus reactants. So delta S equals products 2 times 207 plus 81.2. Those are my products minus my reactants, 181 plus 2 times 11.9. And darn it, I left my calculator upstairs. Oh, no, I brought it with me. Ha, ha, ha. Should always have your calculator with you. So I have quantity 2 times 207, close quantity, plus 81.2, enter, minus 181, enter, and then minus quantity 2 times 11.9. No surprise that anybody distributing this will cost you some points. Don't let it happen. This equals 290.4, and that is going to be positive delta S. That seems strange to me. But let's see here. I've got basically 200. Yeah. Yep. So positive 290.4, and that's joules per Kelvin. Okay. And then find delta H. Same idea. Exact same idea. I'm going to change my color. Oh, I better pick something I can tell the difference with. I go gray. So let's take a look at zinc nitrate. Negative 569. NaOH, negative 470. Zinc hydroxide, negative 642. And then NaNO3, 2 NaNO. So NaNO3 is negative 446. So exact same deal. Oops, I'll let that settle. Exact same deal, products minus reactants. So delta H is going to be my products, which is going to be 2 times negative 446 plus my other products, negative 642 minus negative 569 plus 2 times negative 470. Figures need to give myself an answer for that one. So then I'm going to have 2 times negative 446 minus 642, enter, negative 1534, plus 569, this would be plus 2, plus quantity 2 times 470, close quantity, and I get, negative 25 kilojoules per mole. So on this one, just to make sure, negative 800, negative 1400, negative 8. Okay, that's pretty close to 0. Now to find delta G, what we have to do is delta G, equals delta H minus T delta S. But S stands for S is stupid unit. So do you see how this is in joules per Kelvin? We need to put it into kilojoules. So that means 0.2904 kilojoules per Kelvin. So our kilos have to be simpatico. Negative 25 minus, oh, did it give me a temperature? This up here, I believe, tells us our temperature is at 25 degrees Celsius. I'll remember how it's at the naught. Remember what naught meant? I forgot what naught meant. So let's see here. Degree. I'm panicking a little bit. Oh, and it's not finding it. Oh, isn't that sad? There it is. It has to be at 298K. I thought it was 298K. The weird thing is we've got 298 and then delta S 0.2904. The weird annoying thing is that we've got 25 degrees Celsius for this standard conditions, but then we have STP where it's 0. So negative 25 minus quantity 298 times 0.2904 close quantity. I get negative 112 kilojoules per mole. And that's it for this one. And we're almost done with this part. So to that, I will say toodles.